I guess we could get started. Let me start with introducing the speaker. We are very pleased today to have Professor Siva Theja Maguluri from the School of Industrial and Systems Engineering at Georgia Tech to present our seminar. He is the Fouts family early career professor and an assistant professor at Georgia Tech, before which he was at IBM Watson, and before which he did his Ph.D. at University of Illinois at Urbana-Champaign. His research interests include controls, optimization, algorithms, and applied probability, and he's recently been studying various RL problems. He's recipient of several awards, both for his research as well as teaching. I'll hand it off to him now, and we are going to hear about finite sample convergence bounds. Thank you, Siva.
Thanks, Sanjay. Thanks for the gracious introduction. And I also want to thank you all for attending the talk and for inviting me here today. So I'm going to talk about two pieces of work, which are jointly done with my student Zai Chen, who is the first author on both of these papers. And Sanjay is also a collaborator on one of these papers. And Tin was my former postdoc, who is currently at Virginia Tech. Xing Zhang, Karthik Shanmugan, and JP Clark. So I think I don't need to introduce reinforcement learning because it has become very popular of late because of the success stories that we have seen in many different disciplines. So reinforcement learning was kind of dead for several years before it was reborn with the success story of AlphaGo, when folks at DeepMind built a reinforcement learning system that could beat the best humans at Go. And since then, there have been many more success stories. Of late, people are using reinforcement learning to train robots. There's a lot of work on training robots in simulated virtual environments. And then there's also work on using it in real-world robots. So in reinforcement learning, there's an agent and there's an environment. And the environment is usually described in a state. And the agent, so this is a dynamical system, so it changes with time. At every time, the agent can take an action. And the action does two things. One is it changes the state of the environment. And two is that the agent gets a reward. And the goal in any reinforcement learning problem is to maximize long-term rewards. And this setting that I just explained is identical to what is called the Markov decision process, or MDP, that's very well studied in control theory for decades, if not up to a century. The main challenge in reinforcement learning is that we want to do this without knowing the system model. What is the model? The model describes the transitions from the current state to next state. If I take a particular action, and if I'm put in a particular state, what is the probability of going to each of the future states? These are the transition probabilities. And in an MDP, when we study MDPs, we assume that these transition probabilities are known. But in reinforcement learning, these are not known. And but still, we want to solve the problem of maximizing long-term rewards. And typically, when one studies MDPs or reinforcement learning, one works with a policy. What is a policy? A policy is a rule that maps the current state to an action. So if it says that if I'm in state 0, take action red. If I'm in state 1, take action blue. Or if I'm in state 2, take action red with probability half, action blue with probability half. So the policies can be stochastic. Then in one approach to reinforcement learning is to take a lot of action somehow and then estimate all these transition probabilities. And once we know all the transition probabilities, this problem reduces to MDP, and then we can use MDP algorithms to solve it. That is usually called model-based reinforcement learning. But what is more popular in practice and what led to all these success stories is not model-based reinforcement learning. It is model-free reinforcement learning, where the idea is that I want to find the optimal policy directly. Because at the end of the day, I don't care about the transition probabilities. So can I somehow find the optimal policy directly? And that's what we'll look at. So in the MDPs and in reinforcement learning, something called a value function plays a very important role. So usually in MDPs, we look at the V function. So suppose I'm given a policy. I want to know how good this policy is. And I can do that by finding this value function. So it's a function. For every state, it takes a value. And in this talk, I'm going to focus on finite state and action spaces. So for me, functions are the same as vectors. So I'll use function and vector interchangeably. And so this S component of this value function for a given policy pi is simply the long-term total reward. So I start in state S, and at every time I take an action according to my policy, either deterministic or stochastic. And then at every time I get a reward, I look at my total long-term reward. But as time goes to infinity, my total reward could go to infinity. So I discount it with discount factor beta so that it's all a finite number. and this is my value function. For every state, I can find this. And usually in MDPs, one only works for this V function. In reinforcement learning, it turns out that it's useful to look at something called the state action value function, or the Q function, which is a function not only of current state, but both a function of state and action. And this is very similar to the V function. All I do is at time 0, I start in status. At time 0, I take action A. I don't follow the policy. Then at all other future time, I follow the policy. And then I look at the long-term reward. And by doing this, I increase my dimensionality. Instead of working in S-dimensional vectors, instead of working with S-dimensional vectors, I'm working with vectors whose dimensionality is S times A. So I'm making it worse, but it turns out that using this Q function is very, very useful when we get to reinforcement. And like I mentioned, the goal is to find the optimal policy, the policy that maximizes this long-term reward. This is a vector. What does maximizing a vector mean? Think of it as some convex combination of all the components, some conic combination of all the components, or think of it as a particular component. It can be shown that there is a single policy that maximizes all this. And this is usually called a control problem. And this is the real goal. But many times it turns out it's useful to think of a smaller goal called a policy evaluation problem. Here, the idea is someone gives me a policy pi. All I have to do is find the value function. That's it. I don't have to solve the control problem. Why is this useful? Because there are a class of algorithms called actor-critic algorithms, which are based on policy gradient theorem and so on. We'll not talk about those today. And finding this policy evaluation problem is a subroutine in those problems. That's the reason policy evaluation is interesting. I'll talk about both these goals in today's talk. And one of the central theme, a central idea in the theory of MDPs is what is called as the BELLMAN equation. So it can be shown that the value function of policy pi satisfies the following recursive equation. So V pi of S is my current reward plus the discount factor multiplied by my the value function at my future state. S1 is my state at time 1, and then this S1 can be random, so I take expectation over it. And we're going to explain how we got it and so on, because this is quite well known. And for the control problem, similarly, I can write a BELLMAN equation for the Q function for a given policy pi. I did not show it here. Then for the control problem, remember in the control problem, I want to find the optimal policy. Let's say the optimal policy is pi star, and then let's say its value function is V star and its state action value function is Q star. Then again, I can write a BELLMAN equation for V star and Q star. I did not show you the BELLMAN equation for V star. For Q star, it looks like this. It's again very similar in spirit. Q star is comma A is my current, my reward at time 0 plus my discount factor times my future reward, my value function, my Q star, starting from state S1. But instead of taking a particular action, I take max over all action. And so remember, I want to find the optimal policy. So the idea is that suppose I find Q star, then I can find the optimal policy by simply doing the argmax. That can be proved. So the optimal policy is obtained by simply doing the argmax here. And the reason we use the Q function is because once I know Q star, I can find the optimal policy simply by doing argmax. But if I had used V star, it's not going to be that simple. That idea is not going to work. This is the reason a Q function is used in reinforcement learning. And if you look at this equation, I don't expect you to remember this equation in detail. Every time I need it, I'll show it to you. But the main thing I want you to notice is that this is a vector equation for every S. This is true. The left-hand side is my vector that I want to evaluate. The right-hand side is some function that involves my vector. So this is a fixed point equation of this form. And the key thing to note is that this H operator has an expectation in it. And this expectation depends on my transition probabilities, which I do not know in the reinforcement learning setting. So now my goal is to, in the policy evaluation problem, my goal is to solve this fixed point equation when I don't know the H operator. In the control problem, my goal is to solve another fixed point equation where I don't know the H operator. And so with that introduction, this is the outline of my talk. First, I'll talk about stochastic approximation, which for the context of our talk, you can think of as a method to solve fixed point equations when you don't know the operator, but you have access to a noisy oracle. Then I'll talk about how stochastic approximation can be used to obtain algorithms for reinforcement learning. I'll talk about the policy evaluation problem. In particular, I'll talk about something called off-policy variant of it. And then I'll talk about the control problem. These are the algorithms that I'll talk about, B-Trace and Q-learning. And this will be the major part of my talk, which covers one of the two papers. And if time permits, I'll talk about the Q-learning part in presence of function approximation. Most likely, I think I'll probably run out of time and I'll probably skip the last one. Any questions before I get started? Feel free to stop me anytime if you have any questions or clarifications. Okay, so in stochastic approximation, I want to solve a fixed point of this form, hx equal to x. Obviously, I need some assumption on h for this to work. I'll get to it in a minute. Why am I interested in this? Because I want to solve the BELLMAN equation for reinforcement learning. That's why I'm interested in this. There's another class of problems which fit into this framework, which is optimization. Let's say someone gives me a function f, which is nice enough. I'll not get into what nice means. Basic minimum is convexity. In addition to that, I need smoothness, strong convexity, all those nice things. And then let's say I want to find the minimum of this function. Then I can define an operator that looks like this. It's just x minus some constant times gradient of f of x. Let's say it's smooth, differentiable, all those nice things. Then solving the fixed point equation hx equal to x is same as solving gradient of f of x equal to 0. And finding gradient of f of x equal to 0 is same as optimization. So optimization can be thought of as a special case of solving fixed point equations. In fact, I'm going to talk about stochastic approximation, and in the case of optimization, it's extremely popular by the name of stochastic gradient descent. Okay, and then a simple method to solve for this fixed point equation is to simply do xk plus 1 equal to h of xk. Recursively keep applying this h operator. You can do this if you know the operator. I don't know the operator. I'll get to it in a minute. And does this work? And the answer is it does if my h has a property called contraction. What is contraction? Remember, h is an operator. It takes a vector, spits out a vector. So if I take two vectors x and y, and then let's say there is some distance between them. So I'm only working with d-dimensional vectors, Euclidean space, RD. But Banach fixed-point theorem is true in abstract spaces. And if I apply this h operator, I'll get two new vectors, h of x and h of y. And the distance between them is smaller. It's smaller by a factor gamma, which is strictly less than 1. So whenever I have a contraction operator, if I recursively keep applying it, then Banach fixed-point theorem says two things. Firstly, this h has a unique fixed point. And secondly, this iteration converges to that fixed point. And it does geometrically fast. It converges geometrically fast. And the geometric rate is also called linear rate of convergence in optimization. So this is good, and Banach fixed-point theorem is used in many, many areas. But the problem is I don't know this h. So I can't do this iteration. But what I do have is I have access to an oracle. What is an oracle? I give it x. I give it xk. It gives me h of xk. But it's a noisy oracle. It doesn't quite give me h of xk. It gives me a noisy version. It will add some noise to it. Now the question is, can I solve, does this iteration work? Can I solve this fixed point equation? And so on. And that's what we're going to look at. And turns out there's a slight generalization of this iteration, which is very powerful. And it looks like this. So what this simple iteration is saying is that I'm currently at xk. I ask this oracle for h of x. It gives me h of x plus noise. I blindly go to that point in the future. That's what this iteration is saying. But then if you think about it, this oracle is noisy. Let's say after a lot of time, somehow I think I'm very close to the answer. But then now, if the oracle was exact, then suppose xk was h star, then it should give me h of x star, which is same as x star. I know I'm at the answer. But the oracle is going to give me a noisy version of it. And then if I completely believe in it and go there, then I'm probably going to end up somewhere far away. The distance depending on the magnitude of this noise. So which means I should not trust this oracle too much. So what I do is, I do a convex combination. I'm at xk. I have to go to h of x plus noise. I don't trust the oracle too much, so I go to some point in between. And that between is characterized by this parameter epsilon k. I'm making it a function of k so that I can make up my mind later if I want to change how much I trust this oracle, if I want to change that as time goes. Usually I want to make epsilon k diminishing, decreasing, so that I trust this oracle less and less as time goes on. And in particular, if epsilon k equal to 1, it reduces to the simple Banach fixed-point theorem iteration. And the same thing can be written in this other form. And if you remove h of x minus x and put minus gradient of f of x, that's exactly SGD. Stochastic gradient. Okay. So this is what we're going to analyze. This is called stochastic approximation, which was first introduced by Robbins-Monroe in 1951. And I have to tell you how this noise behaves. In the simplest case, you can think of it as IID mean zero bounded variance. But I look at very, very general noise. So remember, I give this oracle xk and it gives me h of x plus noise. But then the way it adds this noise it can do it in such a way that this noise depends on all the history. It remembers all the XKs that I have given it till now, and then it makes this noise some complicated function of all this. And I can allow that as well, as long as this noise has mean 0, conditionally mean 0. That means this noise is marginal difference. That's what it means. And the variance of this noise, I'm assuming in the simplest case, I can simply assume it's bounded by a constant. But I'm relaxing that, and I'm saying that the variance can actually increase with my XK. And it can increase quadratically. I call this affine bound on the variance. It's affine in X square. Why do I need this? It turns out that I need this assumption on variance to use it in the context of reinforcement learning. That's the reason I make these assumptions. So these are fairly general assumptions on the norm. Okay, let me now state the main results. So in the first, I want to state a simpler result when my step size is a constant. In the next slide, I'll talk about diminishing step sizes. And so far, I was telling you that this H is a contraction. Whenever I talk about contraction, I should tell you under what norm it is a contraction. And this norm plays a very important role. It determines the underlying geometry. And the results that we have are true for any norm. You can take any norm in RG and then our results are true. But for simplicity, I'll state the results only for infinity norm. Why? Because the infinity norm case is by far the hardest case to deal with among all norms. Once we figure out how to analyze infinity norm, it's very easy to generalize to arbitrary norm. And in particular, if we have two norms, then it's equivalent to SGD. Okay, so the theorem says that the step size should be small enough. We need a condition on the step size. I'm not showing it explicitly here. We have all the details in the paper. And then I look at, I want to go to X star. I want to look at rate of convergence. I want to obtain finite time bounds. And so I look at, after time k, I'm at xk, and this xk is random. Why? Because the oracle is introducing random noise. So I look at xk minus x star, mean square error of it. And we bound this using two terms. The first term is nice. It's something less than 1 and power k, which means it's going to 0 geometrically fast. So this is very good. This is inherited from the geometric convergence of BANACH here. But the second term is actually very bad. It's a constant, which means even if k goes to infinity, I'm not converging anywhere. I have this residual noise in steady state. If you think about it, I said that if epsilon equal to 1, I'm just doing Banach 6-point theorem iteration, which means even if I started at x star, because of the noise in the oracle, I will not converge anywhere. I'll randomly keep walking around. Pictorially, it looks like this. I start somewhere, I run my iteration, and then very quickly, geometrically fast, I enter into a ball, so to say. And then once I enter this ball, I'm not making progress anymore. And that is captured by the second term. And the C1, I'm hiding a lot of details in the C1, C2, C3 because I didn't want to show big, long expressions. But the C1 depends on my initial error. If I happen to start with x star, this initial error is 0. And I like to call the first term bias because that is the error due to not starting at the right answer. Obviously, I can't start at the right answer because I'm trying to find x star. As time goes to infinity, this bias usually goes to 0. And the second term, I like to call it variance because that is present due to the noise in the oracle. And the C2 is important because that determines this geometric rate of convergence. And the C2 depends on my contraction factor gamma. And one important aspect of our result is that the constant here depends on the dimensionality of the underlying space. And when we are looking at the infinity norm contraction, this dimensionality dependence is logarithmic in T. It's log D. And this log D is inevitable because intuitively speaking, the reason is that I have infinity norm here. I'm taking expectation of infinity norm square of some quantity. And infinity norm is like max of all the components. If you have D, IID Gaussians, and if you take their max and then look at the variance, you'll get a log D. That's intuitively why the reason we have log D in the case of infinity norm. Okay, good. So any questions on this result? So qualitatively, this kind of results are very well known in SGD community. What we did is we generalized it to arbitrary norm contraction. And but the thing is, I want to find x star. I'm not happy going to this ball. And notice that the radius of this ball depends on my step size epsilon, which means this suggests the following heuristic. I start at my initial condition. and then I use a constant step size epsilon. I very quickly, geometrically fast, I enter into this ball. Once I enter into the ball, I know I'm not going to make any more progress, so I can just simply half my step size. Then I'll geometrically go into this half ball, and then once I enter that half ball, again I can keep halving, and in this manner I can go to X star. So in fact, this idea is used as a heuristic in many practical implementations of stochastic gradient descent and stochastic approximation. The main challenge there is to figure out when you enter the ball and the heuristics to do that. Instead, what I will do in the next slide is I will a priori pick a sequence of diminishing step sizes so that hopefully I don't end up in this ball. Hopefully I eventually converge to X star. So I don't have to figure out when I enter the ball and so on. I'll just in an open loop manner pick my step sizes. And the step sizes I'm looking at are of this form, constant over k power something. And this exponent can be any number between 0 and 1. If it is 0, I get a constant, it reduces to the previous slide. And if it is 1, I get 1 over k step size. And exponent greater than 1 is not allowed, because if it is greater than 1, then my step sizes are summable. And if they're summable, what that means is I can't explore all of my state space. If the step sizes are summable, then starting from my initial state, the total, even if I wait up to infinity, I can cover only some finite ball around that. If X star happens to be outside it, I can't converge to it. So this psi must be 1 or smaller. So we look at all the cases for psi between 0 and 1. And the result looks like this. So in all these cases, I again have the bias term and the variance term. And typically the variance term is slower than the bias term. Earlier, remember, the variance term was a constant. In all these cases, the variance term is actually going to go to 0, but it goes to 0 slower than the bias term. So I'm only showing the dominated rate, the slower rate, which is the variance rate. So if the psi is not 0 and not 1, it's strictly between 0 and 1, then the variance goes as 1 over k power psi. But the bias turns out it has certain exponential form, which I'm not showing here. So this is good. The good thing about this is that eventually I'm converging. I'm converging to X star in mean square sense. But the bad thing about this is that forget about the geometric rate. This rate is very bad. Think of psi is half, for example. Then this is like 1 over square root of k. The mean square error is 1 over square root of k. Then the natural question is, if psi is larger, then this rate is better and better. But this is saying psi should be strictly less than 1. What happens if it is equal to 1? And that leads to the next case. In the next two cases, turns out in the first case, this numerator constant alpha is not that important. It shows up in this constant C4, but beyond that, it doesn't play a very important role. It doesn't affect the rate. But in the 1 over k step size case, this numerator alpha plays a very, very important role. It should be below, it should be above a threshold. If it is above a threshold, then I get 1 over k rate. Otherwise, my rate is affected. So this is phase transition kind of thing at this 1 over k for the 1 over k rate. What this means in practice is that I have to pick this numerator very carefully, and many a time I don't know this C2 in SGD or even in stochastic approximation. So in that case, what you should do is you should probably just stick to this case, first case, and then pick psi equal to 0.99 or some such large number. And again, I hid a lot of details in this constants. This C2 is the same C2 we had before, which depends on my contraction factor. And what I hid in this constant is the dimensionality dependence and also the dependence on my contraction factor. So in particular, for the infinity norm, we have logarithmic dependence on dimension, exactly like before. But in terms of contraction factor, we have the 1 minus gamma cube dependence. And the C6 depends on the initial condition. Questions on the statements, on the theorem statements? Okay, so I want to give a very quick overview of the related work. So firstly, if the contraction norm is the standard Euclidean norm, the L2 norm, and the noise can be affine, then essentially this reduces to stochastic gradient descent of smooth and strongly convex functions. And this is well studied in literature. This is a nice survey paper that I cited, but these results were known much before this survey paper. And if the contraction norm was infinity norm, and suppose the noise is bounded. So in the first case, I made the norm very, very special. The noise is general. In the second case, the norm is general as it gets, so to say. And then, but the noise is very specific. It's bounded. And this was studied in the context of Q-learning. Several years ago, Beck and Srikanth obtained finite time bounds which depend polynomially in D. And then last year, Wainwright has a result where he obtained the logarithmic dependence on dimension. What we did is we allow for arbitrary contraction norm, and the noise can be affine. And we do this motivated not only by Q-learning, but a new algorithm called B.Tech, which I'm going to explain soon. And this is our work, which I just presented to you, and this recovers all the previous results. In particular, for the Q-learning work by Wainwright, he doesn't get a general result on infinity norm contraction. He exploits the special structure of Q-learning in addition to the contraction property to get the results. But then we don't, our results are true for arbitrary contraction operator. And the key thing about our approach is that it's a LYAPUNOV drift approach. And then we came up with a new LYAPUNOV function, which gives this general result. I'm going to show you the LYAPUNOV function in a bit. What I'm going to do next is I'll first show how these results are useful for reinforcement learning. I'll show two applications, and then I'll briefly talk about the proof technique. Any questions? Okay, so let me first talk about the policy evaluation problem. So here there is a policy pi. Someone gave me this policy. All I have to find is I have to find the value function, which the value function of the policy. And then we know that the value function is a unique solution of the BELLMAN equation. And the BELLMAN equation looks like this. S next by S next, I mean the state in the next time. And then this is a fixed point of this form. And then it is known that this H operator is a contraction. Actually, it's a contraction with respect to L2 norm, L infinity norm, weighted L2 norm, L infinity norm, weighted LP norm. It's a contraction with respect to many norms. For the policy evaluation, this is very well behaved. So based on what we learned about stochastic approximation, I can simply do an iteration that looks like this. Vk plus 1 equal to Vk plus step size H of Vk minus Vk plus 1. Then this suggests the TD algorithm. So what is TD algorithm? Vk plus 1. So these are vectors, right? I'm just showing one component of this. I update all the components. Vk plus 1 is equal to Vk plus step size. And then this minus Vk is sitting here. This H of Vk plus noise. Remember, if I did not have noise, this was supposed to be this expectation of R plus beta V next. What I do is I drop the expectation. I simply drop the expectation because I don't know how to evaluate it. The expectation depends on the transition properties, which I don't know in reinforcement learning setting. That's the big problem. So I simply drop the expectation and just take one sample. I just do reward at the next time. Think of this T as 0 for the time being. Reward at the current reward plus beta times V at the next day. Think of T as 0 in this whole thing. This is called TD learning. So TD learning is just stochastic approximation for the BELLMAN equation, where you introduce noise by simply dropping the expectation. Now there are many variants of TD learning. One of them is T-step TD. So what I do is in every time I take T samples, I let this thing run for T time steps, and then usually this bracket term here, this reward plus beta V next minus V, is usually called the temporal difference. And then you add T of these things by discounting them appropriately. And then one can show that this can also be thought of as an appropriate T-step BELLMAN equation. And that also has a nice contraction property and so on. And this is well studied in literature. Why do people study this? Because if T equal to 0, you reduce to the TD that I talked about earlier. If T equal to infinity, this is what is called as Monte Carlo algorithm. And empirically, people found that T somewhere in between is what is actually the best. Okay, this is T-step TD. So this is also quite good. Then I was talking about off policy. What does off policy mean? So the idea here is that I give you policy pi. I let you collect data. So you don't know the model, right? So you have to collect data somehow to estimate the model, either implicitly or explicitly. So you have this MDP system, either your self-driving car or robot or whatever it is. So what you do is you collect the data by following this policy, use that data to update your iterates in this manner, and then that is TD learning. Now what I want you to do is, I want you to do it in off-policy manner, which means I'll actually give you data. You don't have to work hard in collecting the data. But the caveat is that this data was not collected with policy pi. It was collected with a different policy pi prime. Why? Because maybe this data was collected on this robot like 5 years ago by my grad students. And because at that time we thought pi prime was a good policy, he spent like one whole year collecting this data. Now he works for DeepMind. I can't ask, now I think policy pi is a better policy, but I can't go and ask him to collect this data again. He's not going to come back and do it for me. So I want to somehow use this old data to learn the new policy. That's off-policy learning. And this is important in practice, especially in settings such as healthcare, where clinical trials are expensive, and then usually clinical trials are done under some policies, under some treatment regime. And then several years later, if you come up with a new treatment regime, you want to evaluate the new regime using the older data. And typically, what is done is you have to use importance sampling factors. So suppose there are two coins. I give you data collected according to coin pi prime, and then I want you to evaluate the probability of heads of coin pi. Then all you have to do is introduce certain importance sampling correction factors, and then in expectation it will work. And I'll talk more about this in the next slide. So this is exactly the equation from the previous slide. These are the importance sampling factors that I introduced. Typically, in the case of reinforcement learning, the nice thing about these importance sampling factors is that they don't depend on the transition probabilities. They only depend on your policies. The transition probabilities nicely cancel out. That's a good thing. And the policies you know, so you can calculate this ratio of the two policies. Pi prime is the policy that was used to collect the data. It's usually called the behavior policy. And pi is the policy that you're trying to evaluate, which is usually called the target policy. So since you're doing t-step TD, this is little t. So for the little t term, you have to multiply this ratio from time 0 to t. But the problem with importance sampling in general is that it corrects for the bias, so which means it will converge to the right thing, but it can introduce high variance. Firstly, if pi prime is 0 for some action, then you're in trouble. Usually assume that you don't have such zeros. Or let's say this pi prime is always greater than 0, but if pi prime is very small, then this roti can be very large, and then these are noisy estimates of my expected temporal difference. So then this roti can magnify my noise, so I have issues about variance. Then typically one hack that people use is to simply clip these importance sampling factors. What do I mean? I'll take some constant 10, let's say. If my importance sampling factor is less than 10, I'll use it. If it's greater than 10, I'll simply use 10. I'm clipping it at 10. That will solve the variance issue, but it will introduce bias. So usually you have to pick the clip factors in such a manner to trade off this variance and bias. In the context of off-policy TD, there was a very clever algorithm called V-trace, which was proposed in 2018 in a paper called Impala, which was actually an empirical work. They proposed this algorithm and showed how it works in practice, and then this is a very popular algorithm that's used in many, many different applications. So the key idea there was that, so you have all these terms, you have this product of t plus 1 different importance sampling factors, clip the first t of them with one constant and clip the last one with a different constant. Okay, fine, what big deal? I mean, I could have clipped each one with a different constant. Why does it matter? What they showed in the 2018 paper is that the bias that you introduce, so by doing this algorithm, you'll not converge to V pi, you'll converge to something else. That's the bias. The bias that you introduce depends only on rho bar. It depends on the clip factor that you use for the last term. It does not depend on C bar, which means you can pick rho bar in order to make your bias as small as you can tolerate. Then for a given rho bar, you can tune your C bar to minimize the variance. This is the key idea in the V-trace algorithm. So this algorithm was known, and then it was also shown in the 2018 paper that this V-trace can be thought of as a stochastic approximation of certain BELLMAN operator, and this BELLMAN operator has a contraction property. So that was also shown, but they did not obtain finite time bounds. So obtaining the finite time bounds is important to clearly establish this trade-off between the bias and the variance. And using the big theorem that I told you, it immediately follows. So I again have the results for all choices of step sizes, and qualitatively they look exactly like before because I hid all the constants. And I'm just showing the case for 1 over k step size if alpha is large enough. So I just copy pasted the previous results, except that now Vk is not converging to V pi, it's converging to V pi rho bar. If rho bar is large enough, if rho bar is like very, very large, then this V pi rho bar is like V pi. Otherwise, there's an error between V pi and V pi rho bar. And this is 1 over k convergence rate, logarithmic dependence in dimension. Here D is the state space. Here D corresponds to the size of the state space, and then beta is my discount factor. The contraction ratio is same as the discount factor, so I have the dependence on the discount factor as a denominator. And this constant here depends on the initial rate. Any questions on B.Tech? Okay. If not, I'll move to the next part, which is of policy control, Q learning, which is one of the most popular reinforcement learning algorithms. So now I want to solve the control problem, which means I want to solve the BELLMAN equation that corresponds to the optimal Q function, Q star. And again, this is a 6-point equation, and it's known that this is a contraction with respect to L infinity norm. So for the TD case, it's a contraction with respect to weighted L2 norm, weighted LP norm, all these norms. That's a very nice operator. But for Q learning, it's not a contraction with respect to L2 norm. It's a contraction with respect to L infinity norm. Okay, whatever, I don't care what norm it is because I know how to do stochastic approximation for any norm. So I simply do stochastic approximation. This is exactly what I would do. And I use the same idea as before. Each component of Q will be updated in this manner. And this, I introduce noise by simply dropping the expectation. I just copied this and put it here and drop the expectation. So there is, so what is the algorithm? Remember, I want to find the optimal policy, but I'm going to collect data using a fixed policy pi, which is the sampling policy or the behavior policy. So at every time I take action with respect to the fixed policy pi, but I'm not trying to find V pi or Q pi. I'm trying to find Q of the optimal policy. So in that sense, this is called off-policy learning. It turns out that here we don't need to introduce important sampling factors, mainly because there's a max here. I'll not get into the details of why that is the case. But there is one issue that has been sweeping under the carpet all along, which is about synchronous versus asynchronous. So let me talk about it now. So if you look at this iterate, this is actually the real Q learning update that people use in practice. What you do here is that you have your system. At every time at time k, I'm in state sk. I take action ak according to the policy. I go to state sk plus 1, I get some reward. And then I update the sk akth component of my Q function. What about other components? I don't update them. I keep them as is. And then at the next time, I update one more component. So at every time, I'm updating only one component of my Q function. This is called asynchronous update. But then if you look at the stochastic approximation, I had to update the whole vector. So what we do is we don't quite study asynchronous Q learning, the real Q learning. Instead, I study a fake Q learning, which is synchronous update, where I update all the components. So the way I envision this is that at every time, I reset the system in every state, take every possible action, and then take collect one data point for the next state and the next reward. Then again reset it to some state, take another action. So I collect S times a number of data points in every time slot, and then update all the components. This is synchronous Q learning. So in practice, this can be done if you're not doing this in an online manner. The way I described it, it sounds like it's not possible. I can't reset the robot in every state. But in games, for example, this is possible. And then typically, many times people like to separate the data collection phase and the learning phase. So if I have a lot of data, so people do something called experience replay, where they collect a lot of data, and then they put all these data tuples, current state, next, current action, reward, next state, and next action in a bag. And then you can sample from that bag so that you can update all the components. So this is not too far-fetched. This is still doable in practice, but this is not quite the same as the first one. And so we study the second one. We study synchronous Q learning by directly applying our theorem. Studying asynchronous Q learning using our approach is ongoing work. We have some promising results on this, and we should have a paper out in the next month or two. Okay, cool. So once we recognize this for synchronous Q learning, it fits exactly into my stochastic approximation framework. Again, I can plug and play. The reason I work so hard to make sure our results hold true for infinity norm is exactly for this, so that I can use it for Q learning and also for B.Tech. And B.Tech BELLMAN operator is also known to be contraction with respect to infinity norm, unlike TD. And again, I have results qualitatively similar to before. Logarithmic dependence on dimension, cubic dependence on 1 minus the discount factor, 1 over k rate of convergence if this numerator constant is large. Questions? Okay, so I'll very quickly talk about related work. Synchronous Q learning, we didn't make it up. It was studied in literature. I mentioned about Shrikant Beck result earlier. They study it and they get polynomial dependence on the dimension on the state space. And like I mentioned, the Weinreich gets a logarithmic dependence on the state space using a different approach. Our results in the context of Q learning basically reproduce, they match the state of the art results by Weinreich. But Weinreich exploits other properties of the operator, which we don't. And asynchronous Q learning is actually studied in the literature. Beck and Shrikant not only study Q learning, synchronous Q learning, but they also study asynchronous version. And more recently, there are 2 papers earlier this year where they study asynchronous Q learning and improve the dimensionality dependence of Beck and Shrikant. But their perspective is slightly different from ours. They don't look at the mean square error that we've been looking at. They look at high probability error bounds. And VTrace was, like I said, proposed in 2018, but there are no known finite time bounds, and we're the first ones to obtain finite time bounds for VTrace. Okay, so I think I have 10 to 15 minutes. I'll quickly talk about the proof sketch.
I'm sorry, I have a question, if you don't mind. Yeah.
Sure, yeah.
So, so far you talked about the upper bounds that you have driven for this problem, but so we know that for the case that you're analyzing, fixed operators under L2 norm with bounded noise, we know there's a lower bound. So I was wondering if for this specific case that you're analyzing with L infinity norm and you have this affine noise definition, which is more general, I was wondering if there's any known lower bound for this case in terms of sample complexity.
The lower bound in the case of SGD is simply 1 over k, right? The lower bound comes from law of large numbers, Kramer-Rao bound, right?
Right.
So what we have is essentially the same thing. So in terms of time, the lower bound is 1 over k. So usually when we talk about these bounds, we have to worry about the dependence on time, various parameters. So the 1 over k is the best known. So and then the logarithmic dependence, I'm not aware of a formal lower bound, but because of, like I explained, the max of Gaussians is square root of log d. Because of that, I believe that you cannot beat this log d. Maybe it is possible to beat this log d if you change the subjective from infinity to something else. But as long as you have infinity norm contraction and you look at infinity norm mean square error, I believe you cannot beat log d. Then the question is, in terms of the contraction factor, can you beat the cube? I don't know if it's formal lower bound as such, but Weinreich has an argument, like a high-level argument, intuitive argument, showing that this cannot be beaten. This is the best possible. However, in the case of Q learning, for general operators, this can't be bet. But for Q learning, has a follow-up paper where he does variance reduction to improve this. I forget if he improves it to 2 or 1. I think he improves it to 1.
So what I mean by that, for example, for the classic L2 norm under the standard bounded variance, we know that the best rate is achieved by, like, yes, SGD is good, but like accelerated Nesterov can get L over K plus sigma squared over, L over square root K plus sigma squared over square root K. So one term is going down with 1 over K, one term is going down with 1 over square root K, right? So if the noise is not dominant, then you can get a bit, sorry, one is 1 over K squared, one is 1 over K. So you can improve that if the noise is getting smaller. I was wondering if this similar analysis has been done for the case that you're analyzing L infinity norm.
I don't think so. In fact, actually, for the contractions, it's not even clear what acceleration means. I think that is an open problem. I'm not aware of much work here because in optimization, we know what acceleration means. But in the language of this contraction and fixed points, I don't even know what acceleration means. So I'm not aware of any work.
Thank you.
But that's something I was wondering. I mean, actually, once we had this result, there were so many follow-up questions that we made. This is one of those questions in that list, but we are not actually thinking about it yet. By the way, I have a question for you. Maybe I can ask that later. So I was wondering what the point of that 1 over k squared plus 1 over k is, because 1 over k is the dominant thing in some sense, right? So yes, the 1 over k squared is not.
But it depends. Like it depends on the variance. If the variance becomes smaller and smaller, like if you have a setting that L is significantly larger than sigma squared, you can say that that other term could be the. That's the argument that they have. Yeah.
I see. Got it. Thanks. Okay, proof sketch. So, so I want to study the stochastic approximation. Excuse me. Okay, I want to study the stochastic approximation. One way of thinking about it is I rewrote the stochastic approximation in this left box. I send this xk onto the left, I send epsilon k onto the right, and then it looks like this. Now I squint my eyes, wave my hands, pretend that the left hand side of this equation is like a derivative, and then in the right hand side I simply drop the noise. Then I get this ODE, x dot equal to h of x minus x. So how did I write this ODE? I just pulled it out of a hat at this point. I didn't prove anything about it. But this way of doing it can be made very formal. We don't do any of that. So this is called the ODE method. There's a lot of work on stochastic approximation on ODE method. There's a very nice book by Borker from about 10 years ago, where one of the main theorems in his book is that if this ODE is such that it converges to x star, that means that your original stochastic approximation also converges to x star under appropriate assumptions on the noise, on the step sizes, and so on. There's a list of assumptions you have to check. So this is quite well known. Then if you want to follow the Borker's approach, what you would do is you try to show the asymptotic, global asymptotic stability of this ODE. How do you show global asymptotic stability of ODEs? ODEs are dynamical systems. So one popular approach is to come up with a Lyapunov function, Khalil, nonlinear control. And the one Lyapunov function that works for this ODE is infinity norm square. Actually, infinity norm also works. I put square because it's convenient for me to whatever I'm going to tell next. But any power of infinity norm works. And it can be shown that the derivative of this Lyapunov function is basically minus constant times the Lyapunov function. If you solve this ODE, you'll get geometric convergence. This is analogous to geometric convergence in Banach fixed-point theorem. Life is good. Now, I want to get finite sample bounds, but I don't adopt ODE method. So in showing the connection between the stochastic approximation and ODE, making the connection formal, there is a lot of heavyweight machinery that is used. But what I do is I write this ODE on scratch paper. I don't put it in the paper because I don't need to formally establish any connection. What I'll do is I'll come up with a Lyapunov function that works directly for the stochastic approximation, and then study the discrete iteration using my Lyapunov function. A natural candidate is to use the Lyapunov function from the ODE. That's the natural first starting point. In fact, for 2 norm that works. If this was 2 norm contraction, then 2 norm square is known to be a Lyapunov function. And then you can use 2 norm square for the stochastic approximation and it works. That's exactly how LGD analysis is done. Again, I want to stress that we don't use ODE method. We use ODE just for the intuition to come up with the Lyapunov function. In the infinity norm square case, the Lyapunov function does not quite work. And okay, what is my idea? I want to come up with a Lyapunov function using which I can write a recursion that looks like this. What is this recursion? For the moment, ignore the quadratic terms, ignore this epsilon square terms. Then I just have this mk plus 1 is less than or equal to m at time k minus time alpha epsilon k. This is exactly like my m dot less than or equal to minus alpha m. Again, if I send this on to the other side and so on. So this is analogous to the ODE. This is my finite time, my recursion, which is analogous to ODE. Once I get this recursion, all the bonds that I showed you will follow by simply solving this recursion. Solving this recursion is actually pretty straightforward but painful. It will be like 3-4 pages of calculations, but nothing big deal. Okay, good. Now all I have to do is find a Lyapunov function that gives me something like this. The bad news is that the infinity norm square Lyapunov function does not work. Why does it not work? So if you compare this discrete iterate and if you compare the ODE, there are 2 main differences. One is that there is error that I'm introducing due to discretization. In ODE, it's like I'm just using the first order approximation and that's it. Here, because of discretization, I have to worry about second order Taylor terms and so on and so forth. And the second thing is I'm introducing noise. So I'm introducing error due to discretization and due to noise. In fact, all of those are captured in these epsilon square terms. When we do the analysis in the paper, that becomes clear. So if I don't have discretization or noise, I can remove the epsilon square terms, and this is very, very similar to the ODE. Okay, so which means I want a Lyapunov function for which I make the following wish list. My wish list is the following. First property is smoothness. Why do I need smoothness? Smoothness means it's simply like this. If I don't have smoothness, I can simply do Taylor series. I'll have like a lot of terms on the right hand side, or I can do truncated Taylor series. Then I'll have something that looks exactly like this, but instead of L, I'll have a Hessian, and I have to worry about the Hessian. Here I'm simply saying that the Hessian is bounded in command. That is smoothness. So why is this useful? Because this first order term is very similar to the behavior of the ODE, and my error due to discretization and due to noise are all in the second order term. If I can bound the second order term using a constant here instead of a Hessian, then I'll get a handle on the second order terms, and then I'll get this O epsilon squared terms. That's the idea for wishing to have smoothness. And the second approximation, and the second thing I need in the wish list is the following. Suppose I have this recursion. Suppose I find a M that satisfies this recursion. When I solve this recursion, I'll get a bound on M. But I don't know what this M is. I want the bound on mean square error of infinity norm. So what I need is whatever this M is, it better be close to the infinity norm square. So that once I solve the recursion and get a bound on M, I can simply use this approximation property to translate it into bound on infinity norm square. So I need a Lyapunov function with these two properties. If I find it, I'm done. And that's what we did. So the answer for this Lyapunov function is this. So I take my ODE Lyapunov function, I take the guy that I'm trying to approximate. The problem with this infinity norm square is that it's not smooth. If it is smooth, I'm done. Approximation is true with C equal to 1. And the smoothness, if it is smooth, I'm done. But it is not smooth, unfortunately, because of the max. Infinity norm means there's a max. So what we do is we take what is G. G is some smooth function. You can pick any smooth function. The smooth function we pick is P norm square for P between 2 and infinity. And take any smooth function and apply this box operator. The box operator will make the whole thing smooth. That is a property of the box operator. This box is called infimum convolution. And this mu is another parameter which I can use to trade off. If mu is infinity, if mu is 0, then this box is not doing anything. I basically end up with infinity norm square. I'll not have any smoothness, but my approximation will be very good. If mu is something finite, then I'm sacrificing a little bit of approximation, but I'll get smoothness. So there's a trade-off. And what is this box operator? It looks like this. It's take the first function, take the second function, but you have to do this u and x minus u, add them and take the min over u. This is this can be thought of as convolution. Instead of plus, if I had a multiplication here, instead of min, if I had an integral, this is exactly convolution. But I'm working in min plus algebra. So instead of product, I put plus and I put a min here, and this is called infimal convolution. Infimal convolution is known to preserve smoothness, and I use this mu to get my approximation. And the key thing is that there are many other ways of getting smoothness. I can do regular convolution also to get smoothness. But the key in using infimal convolution is it preserves the gradient property also. Infinity norm square was a Lyapunov function for the ODE. But if I did regular convolution, I'll get a new function that may not be a Lyapunov function for the ODE. But using this box, I'll get Lyapunov function for the ODE as well. It preserves the Lyapunov property. And this is not our idea. This is very, very well known in optimization. But in most of optimization, this G is simply chosen to be 2 norm square, which is smooth, strongly convex, all nice things. In that case, it's called Moro envelope. What we use is called generalized Moro envelope. So I think I'm completely out of time. So I'm going to skip the off policy control with linear function approximation. I'm happy to talk about it offline if anyone is interested. So maybe I'll go to my last slide. So I have few other pieces of work in reinforcement learning. One of them is off policy Q learning with linear function approximation. The challenge is that there is something called deadly triad. It can diverge. We introduced a condition and showed that under this condition we have convergence and we obtain finite time bounds. That's one line of work. I have a second line of work on multi-agent reinforcement learning. There are a bunch of agents, and then we look at the policy evaluation problem. They're all taking actions with respect to a policy, but they take local actions, they get local rewards, and everybody wants to find the global value function. And then they only can talk to their neighbors. There's a graph, neighborhood graph, and then they can exchange messages with their neighbors, and they want to find the global value function. And then we came up with a distributed variant of TD, and then obtained finite time bounds for that under function approximation. That's one line of work. And then I have yet another recent line of work on actor-critic-like algorithms. Actor-critic-like algorithms can be thought of as stochastic approximation, but with the 2 scale stochastic approximations. There are 2 iterates instead of 1 iterate, and those are quite challenging to study. And then we have a recent work where we obtain finite time convergence forms of natural actor-critic. With that, this is my last but one slide. I usually stop on this slide. So in addition to reinforcement learning, other areas I work on are resource allocation for cloud computing, wireless networks, data centers, more recently ride-hailing. And then in the context of ride-hailing, I have also been working on pricing for ride-hailing, matching and pricing for ride-hailing. And the distributed optimization work is related to the distributed reinforcement learning that I spoke about. And these are the tools that I use. So I'll stop there. I'm happy to answer any questions.